Yeah, so with that, I'll dive into my talk. Moses already introduced some idea of like some kind of trade-off between validity and breadth, or hallucinations and mode collapse, and I'll be digging down a bit more deeper into that. The purpose of this first talk is mostly to introduce ideas, abstractions, and give you the result, and not give you the proof. The proof would be given by Grigoris in the next talk. It'll take a while, so he'll dive into it carefully. So with that, I'll start. And I'll start by recapping the model very quickly in case there are new people showing up or you forgot what we're doing. So it's a two-player game between an adversary and a learner. There's some collection of languages for this talk. It's a countable collection. And the adversary picks a target language, we'll always call it K, and presents some complete enumeration of it to the learner, one by one. So the learner is shown strings, and the learner's job is to guess a new string from K. So it's not allowed to repeat the strings it has seen so far. And we say the learner succeeds if there is some finite point, depending on all of the choices we have made. So the collection, the target language, its enumeration, after which the learner will always be correct. And again, a few properties. The algorithm is never seeing negative examples here. It's getting no feedback. And for the sake of simplicity, or like for this model to make sense, we'll assume all languages are infinite. Otherwise, at some point, we'll have nothing new to generate. Cool. So this is the core result, or that Kleinberg and Mulanathan showed. It's very clean, very nice. They showed that language generation in the limit is possible for all countable collections. Okay, so this is sort of a starting point, and I want to inquire what it says and what it does not say. Okay, so what it does not say is that the algorithm. It says that the algorithm produces new strings, but it does not say the algorithm can produce all strings in my target language. Okay, so if you want a particular sentence in English to be spit out, like a very good poem, it's not guaranteeing that that like beautiful poem will be popped out. Maybe the algorithm only learned to generate some like naive sentences in English. So pictorially, their algorithm has like operates roughly as follows. There's some target language K at some point. At the start, it generates from some set, this right set. It's a superset of the target language, let's say. And this keeps shrinking. And it has the property that at some point, we go from like having stuff outside of K to having nothing outside of K. And at this point, you achieve like 0 hallucinations, or everything you output is valid. But it just keeps on shrinking after that. Okay. Now, you could ask, like once we go from here to here, why can't we just stop the algorithm here? You know, like call it a day. I have an infinite collection inside of the target language. Let's keep generating. And the caveat there is that doing anything of that sort requires you to identify that you have now become a subset of K, which will tie back to the identification problem and let you identify K in a concrete way. Okay, so that's impossible because of the results of gold. Okay, so this was like, this is not observation by us. Kleinberg and Mulanathan already had observed this in their work, and they asked like roughly this question of like what it means to have some notion of like validity. Is there some trade-off between validity of breadth, or is just an artifact of their algorithm? Or in other words, like what is the limit in language generation in the limit? Okay. So this is what I want to talk about. But yeah, let's maybe try to explore a bit more by what we mean by breadth, or what it should capture and why it's important. So here I have this small picture. The generator is outputting some infinite set in the target language, but it's a very small set. So this generator, I want to say intuitively, has like low breadth, whereas this one has larger breadth, and this one has even larger breadth. So we want like generators with large breadth in some sense. Like ideally, it should just generate everything in the target language except the training data set, which is not allowed to repeat. Why is this relevant? So the idea of generating new strings already captures some notion of that the learner learned something about the target language so that it's able to generate new strings. And I want to argue that like breadth, like the amount of breadth you get sort of captures how much the learner knows. Okay? Now we might disagree on the specific notion of breadth, but for whatever reasonable notion you come up with, if as it increases, like I would like to convince you that it means like the algorithm is learning more and more about the target language. And you know, we want our LLMs to do Like you don't know what people will use it for. You want it to have breadth. You want it to be able to do diverse set of tasks. Okay. And I guess I'll just leave a pointer here to keep you interested. Like towards the end, I'll try to formalize this a bit more with a cute example of why achieving breadth might like imply learning more about the language. It's just a cute like vignette, and like we'll get to that. Okay, so with that, let's get to some concrete definitions of breadth. And again, like feel free to stop me at any point, ask more questions. We have a bunch of times. I want this to be interactive. So to state this, I want to introduce some notation. So for a generator G, I'll represent by G of S the set of strings that it could generate. So like in this model, we have so far defined the game as a two-player game that goes back and forth. Okay? Each time it generates one string. But you could imagine at some point you stop the generator. You're like, okay, I'll not show you more strings, more example strings from the target language, just like keep generating. Like you could have some notion of this generate only mode. And this is the set of strings that it will generate. Okay? So I've been representing the generator as a set so far without specifying what it meant. This is what I mean by it. And then these are perhaps the two simplest notions of breadth you can come up with. Let's go over them. Again, these are just like simple examples to keep in mind. We'll later see how to generalize them, and maybe if you have a specific notion, you can see if that fits into the framework we'll have. So the strongest one and the ideal one you might want is this exact breadth, where the generator denoted by a dotted purple circle is like exactly the same as the target language minus the training set. Okay. You can relax this to have something that for the talk I'll call approximate breadth. It allows the generator to skip like finitely many elements from the target language, right? And you can imagine a spectrum of things in between and like a bunch of bells and whistles on top of this as well, but let's keep things simple for now. So just as an example, suppose the target language is the set of all natural numbers. Okay? And just in case you've forgotten, like, so we think of usually languages as like sets over strings, or something like natural like alphabet maybe, but it's often easier to state examples in terms of numbers, so that's what I'm doing. Like you can always port these things back to some notion of like your favorite encoding into strings. So if the target language is the set of all natural numbers, and my generator generates all things starting from some number I onwards, then it does not get exact breadth. And suppose the training data set does not have like everything from 1 to I, then it's missing something from the target language. It's not getting exact breadth, the first thing here, but it is getting approximate breadth because all it's skipping is the numbers 1, 2, 3 to I minus 1, and those are finitely many. Whereas this generator, which just generates even numbers, does not even get approximate breadth. Just to nail down the definition. And as I mentioned, you can relax this or require additional properties, and there are some works which do that. Okay, I guess I'll stop here. Are there any sort of questions or unsatisfactions about this definition? Because we'll extract them now and try to capture a bit more. Okay, so there are many abstractions you could think of. This is one of the ones we found, which like was particularly amenable to the proof we have. So the proof sort of immediately generalizes to like these sorts of notions, and Grigoris will like give the proof so you can keep this in mind. And it's the property, like for whatever notion of breadth you can come up with, I want to ask the question, a specific generator, let's say achieves breadth for L1, how many other languages can it achieve this notion for simultaneously? So this leads to at least these two abstractions. So I say a property, so now it doesn't have to be breadth, it can be any property you want, of generation has uniqueness if a generator can achieve this property for exactly one language at a time. So just in other words, if a generator has a unique property P for L1, then it can't have the same property for some other L2. Okay? And then I define some notion of finite non-uniqueness. So first I want to say what it is not. It is not that the generator can achieve this property for finitely many languages. It is a different property. It is that if a generator achieves this property for two languages, L1 and L2, then they only differ in finitely many elements. Okay, so it implies what we wanted, but it does not it's stronger. Okay, and this is what we sort of will need if you want the proof to go through. Okay, so let's warm up a bit. Let's see how the definitions we had fit into this framework. So uniqueness, exact breadth, we expect it to have, but here's a simple proof. Let's imagine two languages, L1 and L2. Suppose the generator can achieve exact breadth for both of them, or suppose it achieves one for L1, then it clearly can't achieve it for L2. There's a caveat here, which is the set of the training data set should not exactly be like this set. But if it is, you can come up with a different sort of example. And so in any case, I just want to, regardless of the training data set, you will be able to find you'll be able to find a contradiction to this statement. Okay. And the simple reason is that we required some equality for this set G of S, and it can't be equal to two different things. Something very simple. Okay. So exact breadth has uniqueness. What about approximate breadth? And here's a wrong proof that approximate breadth does not have uniqueness, but here's a wrong proof of the same statement. So we imagine two languages, one subset of the other, and they differ in finitely many elements. Suppose we have a generator that achieves approximate breadth for L2. So it looks like this. And now, so because it has breadth for L2, this region here is finite. But its difference from L1 then is smaller, so it must also be finite. Okay, so this purple set thing gets approximate breadth for L1. It's only missing finitely many elements for L1. But this proof is wrong, and it's not too hard to see. This generator also gets approximate breadth for L2. It does miss only finitely many elements from L1, but it can generate some things not in L1. So it can hallucinate, in other words. So this is bad for us. But there's this easy fix. You can just say that the generator has approximate breadth for the inner language. And now any generator must also be consistent with L2. And because we started with L1 and L2 having finite difference, this goes through. So we have found two languages and a generator that achieves approximate breadth for both of them. So approximate breadth does not have uniqueness. Okay. So now this one I just want to define, but I'll skip over. I'll not give you an actual proof. And I think this is one of the more interesting notions of breadth. So pick any metric you want to evaluate your generator on a language. Okay? It could be the size of the symmetric difference, the sort of thing we have been doing so far. But you could say there's some distribution over my strings, and I want the perplexity of my language model to be low. Or I want the probability mass that it in the symmetric difference to be low, or whatever your favorite metric is. And I say a generator generates unambiguously from K with respect to the collection and this metric if it's a strictly better generator for the target language by this metric than for any other language. Okay? And it's a more abstract notion, but you can show that this also has uniqueness. Okay. So this was just to convince you that whatever this abstraction we came up with can capture some things beyond the sort of set theoretic framework I laid down. So we'll have some consequences for that. And I'm a bit short on time, and I guess by design, so I'll skip this. For finite non-uniqueness, you can get more. You can show that approximate breadth also has this weaker property. And in fact, you can allow, so far we allowed everything to be have no hallucinations. You can allow some hallucinations, and it will still have this finite non-uniqueness property. So it's really going out of some of the set theoretic framework we laid down so far. Okay. So with that, I'll just give you the result that Grigoris will partially prove, and then sort of hand over to Grigoris. So this is the theorem in a couple of parallel papers. If for any language collection L, suppose you have a property that has uniqueness, then you can achieve this property only if the collection is identifiable. Okay? So it's not an if and only if, it's an only if. For many properties, you can get an if and only if, but this is a lower bound. So that's just to say this notion of succeeding in perplexity or succeeding strictly by your favorite chosen metric is very hard. Somehow it makes the problem of generation in the limit as hard as identification in the limit. which we saw is like not possible for even regular languages. Okay, that I think is not a surprising result for exact breadth, like this very strong notion that you need to match the support exactly. But for some of these other notions, it's like, at least for me, it was surprising. And then with finite non-uniqueness, you get some only if with some like slightly weaker condition, which if Grigoris has time, he'll mention, but otherwise it's like slightly complicated to state. But the crux is it's also not achievable essentially for any interesting collection. Regular languages, your favorite enumerable languages, like enumerate, it's not possible. And given time, this would be formalized. The general proof idea here is some sort of diagonalization like Moses did, and Grigoris will do more of it. This result can be extended to the statistical model that Chirag mentioned, like at least the first part, and the second part extend conditionally. I'll not say more. There are more fine-grained notions of breadth, so let's just focus on exact breadth. Then one property we have is Kleinberg and Mullainathan's algorithm. Like sometimes it will get breadth, sometimes it will not, but eventually it will stop getting breadth, always. Like it will never get breadth after some point. So you could ask, is this necessary? So in the previous result I showed it's hard to get, have a diagram which goes from 0 to 1 and always stays at 1. So you get, after some finite time, you always have exact breadth. But you could ask this weaker statement, can you get it infinitely many times, even if you miss it many times? And there's a paper by John Kleinberg and Pan Wei, which shows that this is possible. So they show that, or they construct a different algorithm that has this property. Like, so you sometimes get breadth, you might have to wait a long time, but you'll always get breadth again. So that's just something I'll mention without proof. And here are some sort of interesting questions in this area. There are many more. The first is we define these two abstractions of breadth, but you can look at much more fine-grained trade-offs, and there are some works partially doing this, like including this, like John Kleinberg and Van Wei's work. So there's like, I think, much more to do there. All of our responses, all of our generators so far generate one response at a time. You could think about like some list decodable setting where generator can output more than one thing, as sometimes the LLMs we use do, like they give you two outputs and ask which is better. And that bypasses essentially all impossibility results we have. Like I don't know how much, like whether there's some other proof. And you can ask questions about, we have so far given no feedback, but like humans also, when they grow up, they become old enough, get some feedback in large language models, and like this post-training get feedback. And you can ask, what happens here? What can we learn here? Okay. And for this paper, which I guess I cited a bunch of times, it's going to be presented on Thursday in the language model session. It's by Moses and Chirag, so like be sure to show up. There's some other papers which are relevant also there. Okay. So I mentioned towards the end of my talk, I'll give you a cute example of why having breadth implies learning something truly about the language. So this is that example. Imagine there's some collection which is defined by mathematical axiomatic systems. So for instance, one of the languages in it could be all valid proofs in ZFC. Okay? And the languages have this form. Every string in the language has this form. I have a theorem, space, and then a valid proof of that theorem. So these are my strings. And let our target language be the language which is defined by the ZFC system, or like fix your favorite axiomatic system. And there is a Turing machine that enumerates this language. You can sort of loop over all proofs of length k, try everything. If it succeeds, output it. Like it may not halt, but you can always like do this dovetailing argument and generate a complete enumeration of the language. And now you can go back and be like, okay, can I achieve generation with breadth for this collection? What would it imply? If you could do it, then having any reasonable access to this generator, like say having access to its support, will allow you to check if a theorem is provable, right? Even without knowing the axiomatic system you're working with. You're supposed to learn that from the examples, right? And yeah, this is some like caveat. Okay. So if you found this interesting, like look at it, otherwise skip it, like we won't reference this in the tutorial. Here are the references, and with that I'll hand over to Grigoris. So the question is, do these results carry over to the setting where you're given some prompts, Okay, and short answer is they do, and like it's sort of somewhat detailed in Kleinberg's original paper. So that's the place to look for it, but all of the results I mentioned do extend to that model.
Yeah, so as Anay mentioned, I'll take over and present a couple of proofs, hopefully. But if there's no time, I'm happy to stick to just the first one, the first proof. So the idea of the first proof is to give you a sense of how the lower bound arguments look like in this line of work. And I will instantiate it with a particular lower bound, but it's a general technique which can be used elsewhere. And the second one is this algorithmic approach from this new paper by Kleinberg and Wei, which achieves breadth infinitely often. Okay, so let me just remind you very quickly what is the statement we're trying to prove. So we want to show that if a notion of breadth satisfies the uniqueness condition that Anay mentioned, and the collection L is not identifiable in the limit, then no generator can achieve this property P. Okay, and what is the uniqueness condition? Uniqueness simply says that if a generator satisfies this property for some language at some time, some language L at some time step t, it cannot satisfy this property for some other language other than L. Okay, so we want to make use of the fact that the collection is not identifiable, but so far we haven't told you what the characterization for identification is, so let me go ahead and do that. So Anglin in the 80s, in this like a very foundational work, showed that any collection is identifiable in the limit if and only if every language in the collection has a finite telltale subset. And what is a finite telltale subset? It is a subset, it is first of all importantly a finite subset of L, such that if we look at any other language, L prime, in the collection, if this telltale TL belongs to the language L prime, then L prime is not a proper subset of L. So this might be a kind of hard to parse at first glance, so let me give you a pictorial idea of what this thing looks like. So imagine that we have this blue language L, and someone tells us that this purple set here, TL, is the telltale subset of L. What does Anglin's condition rule out? It rules out the existence of some language L prime, this green language here, that is both a subset of L, and TL belongs to L prime. So this type of sets are not allowed. This type of relationship between L prime, TL, and L is not allowed under Anglin's condition. Is the definition clear? Okay. Okay, so there are a bunch of quantifiers in the definition. So let me try to, what I will use in the proof is the negation of that. So let me just go ahead and tell you what it says. So if the collection is not identifiable in the limit, then it means that there exists some bad language L star, such that no matter which finite subset of L star we choose, we will always find some other language L, such that L is both a strict subset of L star and this finite set T belongs to L. So for this L star, no matter which T we choose, we will end up, we will always be able to find some L for which this picture holds. Is that clear? Okay. So let me go ahead and give you the high-level proof structure, which, as we mentioned before, is basically inspired by Gold's negative result for identification in the limit. What is our goal? How do we show that no generator can achieve this property P? We have to show that given any generator, we can come up with an enumeration E and a target language K, such that the generation does not achieve the desired property P infinitely often. Okay, and as I said before, what we will rely on is that there exists some language L star which shows the violation of Anglin's condition. And then, starting from L star, we will choose the enumeration and the target language via some diagonalization argument by applying this negation of Anglin's condition on L star repeatedly. Okay, and how does the diagonalization look like? I want you to have the following mental picture in mind for the remaining of the proof. So we start by enumerating the language L star. This is the bad language which we will make use of. The adversary starts enumerating this language. So now at some point, the generator might figure out that, okay, I have to do something good with respect to L star. So let me try to satisfy property P with respect to L star. Okay, if this happens, the adversary now switches their mind and they say, okay, they will be like, okay, this is not what I'm enumerating now is not L star. It's actually this language L1 prime. I will tell you later how to define this, how we will find this L1 prime. But there's some special language L1 prime, which is a strict subset of L star, which will be useful for us. Okay, now the adversary continues on to an enumeration of L1 prime. If at any finite time step, the learner tries to satisfy the property P with respect to L1 prime, the adversary will go back and start enumerating L star again. And this thing will go on for potentially infinitely many time steps. So what we will end up doing by this type of diagonalization argument is that we will be able to present an enumeration of some language K from the collection. I haven't told you yet which one it is, but it will be one of the languages that appear in this graph. And we will also be able to make the generator miss the property P for infinitely many time steps. Okay, so in the remainder of my presentation, I will try to explain how we will come up with this type of bipartite graph for our argument. Okay, so the first step is the enumeration of L star. So assume now for simplicity that L star contains the elements x1, x2, x3, so on and so forth. So the adversary starts enumerating these elements, and then at some time step t equals 6, we have this enumeration. Now, if the generator never satisfies the property P for L star, then we are done. This is like the very easy case of the argument. We have already witnessed some bad language K for which the enumerator does not satisfy P infinitely often. So we don't have to do anything else. However, if there is some time step, let's call it T1, for which the generator is actually able to achieve this property P for L star, we will have to work harder. And what we do now, we do the following. Since L star is this bad language which witnesses the failure of Angloin's criterion, we will pick this set ST1 and we will pretend that ST1 would be the telltale set of L star. Okay, so what happens now? Since L star does not have a telltale set, there exists some other language, L1 prime, which both contains ST1 and is a subset of L star. Is it clear why we can do that with L star and ST1? Okay. Okay, so now at time t1, what I want you to notice is that the generator cannot achieve the property P for the language L1 prime, since by assumption it achieves the property P for the language L star. Otherwise, we wouldn't have switched the enumeration. Okay, so why can we switch to the enumeration from L star to L1 prime? The reason we can do that is that so far we have enumerated elements up to time step t1. We have enumerated elements that belong to L1 prime. And L1 prime is a strict subset of L star. So in the next steps, we will skip some elements. Potentially, we will skip xt1, xt2, and then we will end up enumerating this, this blue element here, xt1 plus 3, because the previous ones do not belong to L1 prime. Okay, so this is the idea of the first transition. So what happens after that is that if there exists some time step t2 greater than t1, for which now the generator figures out that we are trying to trick them, and what we are doing actually is enumerating L1 prime instead of L star, and they try to achieve property P with respect to L1 prime, we will swap back to L star. And how do we swap back? We swap back by trying to fill in the holes that we left behind. So we started enumerating L star, we switched to enumerating L1 prime. So when we did that, we left these holes behind. This guy was not enumerated, this guy was not enumerated, so on and so forth. So we will start patching up the gaps in order to end up potentially creating an enumeration for L star and not L1 prime. Okay. So by repeating this argument inductively, we will show now that we can see now that the generator cannot achieve the property P for the language L star at time step t2. This will keep on going for potentially infinitely many time steps. And we will end up, the remaining of the argument is the following. If there are infinitely many phases for which we do the switch between the two sides of the bipartite graph, then what we end up enumerating is this language L star by just going back and forth and filling up potential gaps that we're leaving behind in enumeration. Okay, but now notice that whenever we make a switch, whenever we do a full back and forth in this bipartite graph, we end up creating a phase for which the learner does not satisfy the property with respect to the language L star. So we mark that as a success for us. This is a time step in which we witness that P is not satisfied for the language L star, which we end up enumerating. This is essentially the hard part of the argument. The easy part of the argument is that we might, at some point, end up stopping at some node in the bipartite graph. We might not end up making any transitions from that point on. So what happens then is that since we didn't make any transitions, the learner never satisfied the property P for the language that we were pretending that we were enumerating. And this is the easy case for us because we will show that from this point on, the learner does not satisfy the property. Otherwise, if it satisfied the property at any point, the adversary would have moved, and we would be in the case where we have infinitely many transitions. Okay. Are there any questions about the idea of the argument? The details might be a bit hard to follow on the fly, but I guess what I want you to take out from that is that we have this infinite bipartite graph, we go back and forth, and then what we end up doing is that every time we do this back and forth, we can write down a time step in which the learner fails. This is the main idea. Okay. So with that, let me maybe quickly go over the algorithm that generates in the limit with breadth infinitely often, which is a modification of the previous algorithm by Kleinberg and Mulanathan. So just to remind you, what the KM algorithm does is that at time step t, it creates this chain of critical languages, and then it generates a string from the last language in this chain. Okay, an alternative way to think about this algorithm is that it produces a sequence of indices, and it has the guarantee that after finitely many time steps, all the indices it outputs correspond to languages that are subsets of the true one. So it never outputs the index of a language that contains elements outside of the true target K. Okay, so in order to get the results in the Kleinberg way paper, the main idea is to add a backtracking step in a controlled way. And since we don't have too much time, let me just sketch how this thing works. So in the original KM algorithm, think about this type of chain. So after as Moses mentioned, after some finite time step, the prefix of the chain will essentially remain stable. So all the languages that come before K that appear in the chain of critical languages will stop changing. However, all the languages that appear in the chain of critical languages after K will keep changing forever. All these languages are subsets of K. So as the adversary is enumerating K, these languages will keep on getting contradicted from the data. We will be doing that for infinitely many time steps, essentially. So the main observation of Kleinberg and Way is that whenever a language is contradicted, we basically get some type of free lunch. Whenever a language is contradicted, we can backtrack to the previous one that was not contradicted before. And pictorially, it looks like that. So we have, again, the same picture as before. We have the same chain of critical languages that is descending, essentially. So when this guy is contradicted, instead of outputting the index of the largest critical language, we will end up outputting the index of the language that came before it. We will end up outputting the index of the critical language that remains critical after someone is contradicted. So the backtracking here will end up pointing to k. And that was probably very fast. So again, the main idea that I want you to take away from that is that the original KM24 algorithm keeps losing breadth. The results that Anay mentioned show that this is basically inherent. It has to be losing breadth for infinitely many time steps. However, this new modification shows that it can also keep achieving breadth for infinitely many time steps. So there is something to be gained. Okay, and with that, I'll hand it over to Charlotte.